Hello, I'm Daniel Acuesta and I'm going to discuss on how to find the inverse of a matrix using Gauss-Jordan method. Let's discuss what is Gauss-Jordan method. By definition, the Gauss-Jordan method is a variant of Gaussian elimination in which row reduction operation is performed to find the inverse of a matrix. To put it simply, the Gauss-Jordan method allows us to calculate the inverse of a matrix by performing elementary operations between its rows and puts a matrix in a reduced row echelon form. With this approach employs this formula, having on the left side the original matrix and on the right side the identity matrix. We can now consider this as augmented matrix, which are any elementary row operations that are performed are equivalent in both sides respectively. So in order for us to find the inverse of a matrix, we must make the original matrix into identity matrix. By performing elementary operation on the original matrix, we'll have resulting of identity matrix on the left side, and whatever on the right side is, we can now conclude that it is the inverse of a given matrix. So how do we perform the elementary operation? An elementary operation on a matrix is any of the following. These are the operations we can do with the rows or column in a matrix. The first type of operation, which is interchanging rows or columns I and j of a matrix. The second type of operation, we can multiply a row by a non-zero number. And the third type of operation, we can add or subtract a multiplied row to another row. Later on, we will apply these elementary operations to calculate the inverse of a matrix for you to better understand how they work. Let's proceed in the practical method in finding the inverse of a matrix. In order for us to utilize practically the Gauss-Jordan method, here are the key procedures that can be followed in finding the inverse of a matrix. First, search by identifying the maximum pivot point or the element with the largest absolute value. Second, interchange by swapping the row of the maximum pivot with another row. This is only necessary so that the pivot point is located in the diagonal. Third is normalize by dividing all elements of the maximum pivot row by the value of the maximum pivot. Fourth, eliminate by making the elements of the pivot column except for the pivot be equal to 0. Remember that we can repeat and skip some of these steps or procedures in finding the inverse of a matrix. Now let's apply the methods we discussed earlier. Here is problem 1. Find the inverse of the given matrix with the following values 1, 2, 1, 1, 3, 2, and 1, 0, 1 using the Gauss-Jordan method. Applying the formula we introduced earlier, we have the original matrix on the left side and the identity matrix on the right side. Applying the procedures, we can identify that the maximum pivot point is in the correct position just like the identity matrix. Therefore, we can skip the interchange of rows and the normalization of the maximum pivot rows and continue on proceeding to eliminate the second and third element of the first column with the following equations. R2 is equals to R2 minus R1, R3 is equals to R3 minus R1. Therefore, applying 1 minus 1, 1 minus 1, and the rest of the elements of the rows follows because of the augmented matrix. We now then have the first column of the identity matrix. Now continuing on the second column, we can identify that the maximum pivot point is already in the correct position just like the identity matrix. We can now proceed on eliminating the first and third element of the second column, applying these equations. Row 1 is equals to R1 minus 2 times R1, row 3 is equals to R3 plus 2 times R2. Continuation of solution, we have the result from the elimination earlier. The first and second column of the identity matrix. We now then move to the third column, identifying the maximum pivot point. We can see that it's not the same as the identity matrix. In this case, we can normalize it by dividing the maximum pivot row with the value of maximum pivot. Having this equation, row 3 is equals to R3 divided by 2. Applying the equation, we have this result. We have now the maximum pivot point of the identity matrix. We can now then proceed on eliminating the first and second element of the third column with the following equation. Row 1 is equals to R1 plus R3. Row 2 is equals to R2 minus R3. Upon applying the equation, we now then have the identity matrix. So at this point we have the matrix identity on the left side, which means on the right side we have the inverse matrix. Therefore, the inverse matrix of A is equals to 3 halves, negative 1, 1 half, 1 half, 0, negative 1 half, negative 3 halves, 1, and 1 half. Let's now have another example problem, problem 2. Find the inverse of the given matrix with the following values: 0, 1, negative 2, negative 1, 0, negative 2, 0, 2, negative 3, 0, 1, negative 2, 0, 3, 0, 1, using the Gauss-Jordan method. Applying the formula, we have the original matrix on the left side and the identity matrix on the right side. As we can observe, the maximum pivot point is on the third row. In this case, we can apply the interchange of row 3 and row 1. Upon applying, we have a new set of matrix, and then we can now proceed on normalizing the first row with the maximum pivot value, having the equation of row 1 is equals to negative R1 divided by 3. Continuation of solution, the result of normalization from the previous matrix, we have the first column of the identity matrix. Moving on the second column, we can see that the maximum pivot point is not the same as the identity matrix. Therefore, we can proceed on normalizing the maximum pivot row by the maximum pivot value, having the equation of row 2 is equals to negative R2 divided by 2. Then applying this equation, we have now the maximum pivot point for the second column, and then proceed on eliminating the third and fourth element of the second column, having the equation of row 3 is equals to R3 minus R2, row 4 is equals to R4 minus 3 times R2. We have now the second column of the identity matrix. We can now continue on the third column. As we can see, it's not the maximum pivot point is not the same as the identity matrix. Therefore, we proceed on normalizing, having the equation of row 3 is equals to negative R3 divided by 2. Continuation of solution from the normalization of the previous matrix. We now then have the maximum pivot point of the third column. Let's now proceed on eliminating the first element of the third column. We have the equation row 1 is equals to R1 plus 1/3 multiplied by R3. We have now the result of the third column of the identity matrix. And for the last column, the maximum pivot point is not the same as the identity matrix. We can now proceed on normalizing, having the equation of row 4 is equals to R4 divided by 4. We have now the identity matrix for the fourth column. And continuation of elimination, we can now proceed on eliminating the first and second element of the fourth column by having the equation of row 1 is equals to R1 minus 2/3 multiplied by R4, and row 2 equals to R2 plus R4. And now we have continuation of the solution. We have now the identity matrix on the left side, which means on the right side is the inverse matrix. Therefore, at this point, the inverse matrix of A is equals to 1, 6, negative 1/3, negative 1/3, negative 1, 6, 0, negative 1/8, 0, 1/4, negative 1 half, negative 1/4, 0, 0, 0, 3, 8, 0, 1/4. This is the end of my presentation. I hope you learn a lot, and thank you so much for listening.